Hello, I'm Mr. V. I'll be instructing you for the next few lessons. Part 4, Scale Factors and Areas of 2D Shapes. Review of area of some two-dimensional shapes. Okay, so below I have a whole bunch of shapes for you, and let's just review what the area formulas for these are. So first off, we have a triangle, so remember area equals 1/2 base times height. Some of you might remember base times height divided by 2. They're exactly the same thing. Okay, area of a rectangle. Usually we say length times width, but in this case we have width and height, so that would just be them multiplied together. I'm just going to put in brackets here length times width because that's what we know a little more commonly. Okay, for a trapezoid down here, the area is the base 1 plus base 2 divided by 2, so the average of the bases times the height. Okay, for a square, okay, what we've got is area equals the side length squared. Okay, for a parallelogram like this, okay, it's just like a rectangle. The area is the base times the height, or the length times the width. Well, we actually need the right angle height. That's that h in there. So that is just base times height. Okay, and the area of a circle, of course, is pi r squared. Awesome. So let's determine the area scale factor. Okay, so you remember last lesson, we learned the linear scale factor. We just called that k. So remember, k is a number that is what of the polygon to determine the reduction or enlargement of the shape. Well, k is simply the number that is multiplied to the side lengths. So multiplied to the sides. Sides or side lengths. Okay, to determine the reduction or enlargement of the shape. Okay, the following investigation demonstrates what will happen to the area if we enlarge or reduce a shape by a factor of k. All right, so quick little investigation here. Okay, part A, consider two similar rectangles below. Okay, the scale factor is 2. I'm just going to tell you that right off the bat. Okay, so if the scale factor is 2, that means we multiply each of these side lengths by 2. Oh, look, 20 times 2 is 40. Yay. 8 times 2 is 16. So you can see that the scale factor is 2. So k equals 2. Perfect. Just erase that really quick. Okay, great. Okay, calculate the area of both rectangles. So, okay, well, that's easy enough. So area, we said, was length times width. So 20 feet times 8 feet. Okay, so when we multiply that out, we get 160 square feet. So remember, that's feet squared. Wow, that's really bad writing. I'm so sorry. Okay, so 160 square feet. Okay, so for the longer or bigger rectangle, okay, so area again is length times width. So the length this time is 40 feet times 16 feet. And when we multiply those together, we get 640 square feet. Okay, so good. We've got the area of both rectangles. Okay, so now we want to divide the larger area by the smaller area. Okay, so that seems easy enough. Okay, so we'll go 640 square feet divided by 160 square feet. And what we notice when we do that, okay, that the units cancel, and 640 divided by 160 is 4. Okay, so what is the ratio of the areas? Well, the ratio of the areas is 4 to 1. Oh, okay, well, that's interesting. Okay, so let's go back up to our little sentence here. The scale factor is 2, since the larger rectangle is 2 times as long and 2 times as tall. That is, the lengths have a ratio of 1 to 2. Okay, yet the area of the larger rectangle is 4 times bigger, or the ratio is 4 to 1. So let's just say 4 times bigger. Okay? Interesting. So the scale factor is 2, but the area is 4 times bigger. Interesting. Okay, well, we'll tie that in here in a second. Next page, part B. Okay, so look at these two triangles. Explain why these two triangles are similar. Okay, remember, similar shapes have the same shape, or the ratios of the sides are the same, that kind of thing. So we can just trust that these are similar, but we should, try and figure it out. Okay, so if we figure out the ratio, let's go 12 to 8. So 12 divided by 8. Okay, so that is 1.5. So the ratio of this guy, the blue triangle side lengths, is 1.5. Then if we go 30 divided by 20, oh, look, it's 1.5. So that's why the two triangles are similar. The ratios of the side lengths are the same. So I guess we could write that. The ratio of the side lengths is the same. Okay, so that is number 1. Okay, so that's why they're similar. Okay, so what is the linear scale factor? So what do I have to multiply the 12 to get to 30? Okay, well, that's not always easy, but remember there's a formula for this. K is the image divided by the original. So let's call the small guy the original, and then the red guy the image. So if I take the image size, so 30 feet divided by 12 feet, okay, that's going to give me my linear scale factor. Okay, and when I type that in, I get 2.5. Nice. Okay, now let's actually make sure that this works, because K should also then be 20 divided by 8. Okay, so 20 feet divided by 8 feet, and oh, look, that is also 2.5. So that could also explain why the triangles are similar. They have the same scale factor. Okay, so ratio of the side lengths, scale factor, same thing. Okay, so linear scale factor is 2.5. So K equals 2.5. Great. Okay, so what is the area of the left triangle? So that's the blue guy. So area is 1/2 base times height. So 1/2 times 12 feet times 8 feet. Okay, and when we multiply that into our calculators, we get 48 square feet. Perfect. Okay, the area of the larger triangle, 1/2 base times height again. So 1/2 times 30 feet times 20 feet. When I multiply those together, I get 300 square feet. Perfect. Okay, so that is the number 3. Okay, so what is the ratio of their areas in decimal form? Okay, so we could use fractions on this if I really wanted, but it says decimal, so we're going to just do it that way. So the ratio of the areas. Okay, so that just means I divide the areas. So we're going to go 300 square feet divided by 48 square feet. Okay, so I guess we could call that like the ratio. Okay. Okay, so 300 divided by 48 is 6.25. Okay, remember the feet cancel, and the square feet cancel. So this is a unitless number, the ratio. Okay, so now What do you notice about the linear scale factor and the area scale factor? Now, it's not as obvious here. It's slightly more obvious in the last one. Remember, the scale factor was 2, okay, and the area scale factor was 4. Now, all right, anyways, I guess the idea here is if you take 2.5 and you square it, that is 6.25. Huh, interesting. If we took the scale factor before, like in part A, the scale factor was 2. And if we square 2, we get 4. So the idea here is the area scale factor is just the linear scale factor squared. Awesome. So from the investigation, we can conclude that if two 2D shapes are similar and their dimensions are related by a scale factor k, then the relationship between the area of the similar shape and the area of the original shape can be expressed as, okay, so the area of the similar shape, so we'll call that the area of the image, wow, bad writing again, is equal to the linear scale factor squared times the area of the original. Nice. So then by manipulating the formula above, given that the area of a similar 2D shape and the area of the original are known, then the scale factor k can be determined using this formula. So if I just want the k squared, I just divide by the area of the original. So this is going to be the area of the image divided by the area of the original. Okay, and really we shorten that to just AI divided by AO. Okay, now let's just do one more little quick bit of algebra. If I ever want to find just k, remember it's k squared, so I would have to square root. Whatever you do to one side, you do to the other. So k would just be the square root of a area of the image divided by the area of the object. All right, interesting. Next page. So, example 1. An area scale factor can apply to any shape provided you have at least 3 of the quantities, areas or lengths. Okay, so the solution here, okay, to find the area of the large triangle, you need to find the linear scale factor. Okay, step 1. In general, to find the linear scale factor, divide the larger length by the smaller length. Okay, so if I want the linear scale factor, I'm going to take my larger length, so 6 centimeters, and I'm going to divide that by the smaller length, 4 centimeters. Okay, in this case, I'm going to get 3 over 2, or 1.5. Okay, sometimes it's easier to work with fractions, sometimes decimals are great too. Okay, so step 2, find the area scale factor by squaring the linear scale factor. Okay, so the area scale factor, is 1.5 squared. Okay, so 1.5 squared is 2.25. Okay, and then we simply multiply the area scale factor by the small area to find the large area. So here in this triangle, the small area is 12. Okay, so we go 12 centimeters squared times 2.25. Okay, and we end up with 27 square centimeters. Okay, so if we know the linear scale factor, we can use that to find the new area. All right. Awesome. So example 2. Determine the area of each figure after it has been enlarged by a scale factor of 2. Okay, so we have a little bit of work to do. We can just do some counting for a lot of these. We have to, think a little bit here. So tell you what. So we make these two triangles, and we'll make this guy, kind of cut that off. Okay, this guy here, remember that's a triangle. Area is 1/2 base times height. So the height is 2, the length or the base is 1. So area equals 1/2 base times height. So 1/2 of 1 times 2. Hey, wait a second. That is just 1. So 1 centimeter squared. So look, if this guy is 1 centimeter squared, then this triangle is exactly the same. So he's also going to be 1 centimeter squared. So this is 1. This guy is 1. And look, these whole squares are 1 square centimeter. Okay. Let's go up to this top triangle first. Okay, so area again is 1/2 base times height. So let's see, 1/2. The base is 1, 2, 3 centimeters, or units, I guess. We can call them centimeters. Okay, 3 centimeters, and then the height is 1 centimeter. Okay, so 1/2 times 3 times 1 centimeter is 1.5 centimeters squared. Okay, so let's see, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then this is 1.5, so 11 and 1.5 is 12.5. So the area, that was a lot of work just to figure out that. So 12.5 centimeters squared. Okay, easy enough. Now, if the new object is enlarged by a scale factor of 2, okay, that means the area of the image is equal to k squared times the area of the object. Okay, so the linear scale factor is 2, so 2 squared times the area of the object, well, that's 12.5 centimeters squared. So remember, it's going to be 4 times bigger. So we just go 4, 2 squared is 4, times 12.5. Okay, and 4 times 12.5 is 50 centimeters squared. So that is the area of the image, the new object. Okay, what if it's reduced by a scale factor of 1/3? Sorry, what's this new guy here? Okay, so we've got to figure out the area. So remember, we have an area of a circle, so that's pi r squared. So look, the radius of this thing is, okay, that's half, so that's 1.5. So pi, you can use your pi button on your calculator, 3.14, but use the whole thing, it's more accurate. We're going to round to the nearest, I don't know, 100th anyway. Okay, and then the radius is 1.5 centimeters squared. Okay, so I'm going to use the pi button on my calculator, and anyways, I get an area of the circle 7.07 centimeters squared. And then, of course, the triangle area equals 1/2 base times height. Okay, so 1/2, the base is 1, 2, 3 centimeters, and the height is 1, 2, 3 centimeters. So 1/2 times 3 times 3, so that is 4.5 centimeters squared. Okay, so the area total, or the area of the object here, so 7.07 plus 4.5, so that's 11.57 centimeters squared. Okay, so the area of the image is supposed to be the scale factor squared times the area of the object. Okay, so we have 1/3 squared. 1/3 squared times 11.57 centimeters squared. Okay, and when I type that in, now remember, the 1/3 should be in brackets, okay, when you square, just to make sure that squared goes to the top and the bottom. But when you do this, so let's type it in, and you get 1.23, whoops, sorry, 1.23 centimeters squared. Fantastic. All right. So let's do a few examples, and we'll be on our way. Okay, number 1. A rectangular display with the dimensions 2 meters by 3 meters is located in the lobby of City Hall to show the citizens the layout for the new People's Park. The display was created using a scale ratio of 1 to 120. Okay, the Parks Department estimates that the city spends 75 cents or $0.75, okay, per meter squared to maintain the park from spring through fall. Okay, estimate the cost to maintain People's Park. All right. So really what this means is we need to know the area of People's Park. Okay, so the scale factor here, K, is 120. That's what this ratio up here means. Okay, so the area of the model, if you will, or the object, okay, is 2 meters by 3 meters. So 2 by 3, so that is 6 meters squared. Okay, so the real park is enlarged by 120. So we have to go the area of the park, or I guess the image, okay, is K squared times the area of the object. So K is 120, so 120 squared times the area of the object or the area of the model, so that is 6 meters squared. So 120 squared, that's a really big number, times 6. So when we work through that, and just type it into your calculator, give you a second, and that works out to 4,320 meters squared. Perfect. Okay, now we're not done. That's the area of the park. But to maintain the park, it costs 75 cents per meter squared. So the cost is simply the area times the cost per meter squared. So 75 cents per meter squared. And what happens when you do the math here, the meter squared and the per meter squared cancel, leaving us with just dollars. So that's kind of handy. So when we multiply these, we get $3,240. That's how much it costs the town or the city to maintain or cut the grass and that kind of stuff, trim the trees, that sort of thing. So that's how much it costs for them to do that between spring and fall. So B, a rectangular model with the same dimensions was used to represent Meadow Park. Okay, sure, Meadow Park game. Okay, the scale ratio used here was 1 to 250. So estimate the cost to maintain Meadow Park. Now you can see it's 1 to 250, so Meadow Park is quite a bit bigger. Not just quite a bit, like a lot bigger. Okay, so the area of the object or the model is still 6 meters squared, because it's got the same dimensions. So this time area equals, okay, so this is 250 times now, squared, times 6 meters squared. Okay, so the real area of Meadow Park is 375,000 square meters. Wow, that's huge. Look, this guy, he wasn't that big, but this one, that is absolutely huge. I'm just going to check my math again because, it's always best to do so. Yep, 375,000. Wow. Anyways, and then, of course, the cost for this is 0.75 per meter squared times 375,000 square meters. Okay, so when you multiply that, okay, these numbers are huge, but that's okay. $281,250. So for cities to have huge parks like this, it costs them a very, very large amount of money to maintain these things for the public. That's what your tax dollars go to. Okay, interesting. Okay, number 2, determine the scale factor that relates each pair of similar shapes. Okay, so the area here for the small one is 5. The area of the large one is 11.25 centimeters squared. And we want to know the scale factor. We want to know the K. So remember, K, these are areas, so it's K squared is equal to the area of the big one divided by the area of the small one. Okay, well, that's great. So let's just type that in, 11.25 divided by 5.00. So K squared is equal to 2.25. Awesome. Remember, the centimeter squared cancels. Okay, so now, in order to get rid of the squared and leave me with just K, I have to square root both sides. So then K, so the square root of 2.25 is 1.5. And just type that into your calculator. So the scale factor is 1.5. Fantastic. All right, I want you guys to practice this material by going to page 479, and I would like you to do these questions. Thank you very much. See you next time.